So thank you, and thank you everyone for giving me this opportunity to speak at Notes 2023. And today's topic of discussion is graph algorithms for privacy and fairness in the healthcare industry. And this is Sharmistha, and I'm a 2x Google developer expert on cloud and ML, and I work as the head of advanced analytics chapter area for Commonwealth Bank of Australia. So, to get started today, what we would see is the first agenda. We have several sections and we would cover the following topics. First of all, we will have an introduction to graphs and responsible AI in the healthcare industry. Then we would talk about privacy in graphs, fairness in graphs, and then getting to know how to apply responsible AI with graph neural networks, concluding thoughts with a live use case demonstration. Said this, let's get started and try to understand why at all is graph algorithms are important for healthcare industry and where the role of responsible AI lies. So we have all been knowing it from past sessions in Notes 2022 that how graph algorithms have played a vital role in medical treatment, starting from visualization, giving the prescription of for the patients, the analysis, patient claims, the insurance analysis, patient's diagnosis, and updating that models at different states of time based on the diagnosis, the medicines that have been prescribed to the patients, and on the level of patient recovery. How the patient connects to the entire 360 system of the medical providers ecosystem, be it doctors, nurses, or care providers. How does the entire ecosystem works? Graphs plays a vital role, and therein, having played a vital role of in the medical science, the graphs also show that we need to follow it in a responsible manner. So let's see. So if you see a typical patient flow journey where a patient goes to a doctor and a doctor prescribe medicines after the diagnosis, there are different states involved. First of all, a patient would like to know that the initial health checkup treatments, or in a patient has been diagnosed with a certain sort of a disease. Then what is the medication that is given to the patient, and the next state of how much the patient has recovered, and followed by what are the corresponding the subsequent sort of medications that is given, and how there is a constant interaction between the patient and the doctor or the care provider systems in the mode of the recovery of the patient. And also, not only it's the only the healthcare providers, but there are third parties also involved in the process, be it insurance or be it your home nursing or other services that you are availing at home. So, to have these different states, we need a well-defined structure or a mechanism to track the previous state to the next state, and there where the graphs comes in, and the graphs helps us to visualize it and also to see that what different states that we need to show the information to the public world, and at what different stages that we need to anonymize the information at different nodes, or we need to anonymize the information that the between the ages that connects the different nodes. And we also need to see that coming from the healthcare industry, we need to recommend people to go to different healthcare centers or different doctors, and different kinds of medications, and for the use of the doctors, that they know that this sort of patient history will follow to this sort of medication. So for the benefit of the doctors also, we need to have an historic or a lineage that would help the doctors to understand. So why this foundation pillars of responsible AI comes in from the graph is because we cannot disclose protective sensitive information, like I may have a heart disease or I may have a very confidential disease, right? I may not want to disclose that to the outer world, and that's obvious for any healthcare data if you see. And also, when we train the algorithms, graph algorithms, are we having sufficient data that we are training these algorithms without being biased to a particular race or ethnicity or even a minority? It could be gender, or it could be other sections of other minority groups, like lesbian or other other genders that we can think of. So what we need to focus on is how we measure the similarity or the difference in treatments that we are offering to the majority section of the population as well as the minority. So are we able to see that the error in our treatments or the error in the diagnosis is the same for different sections, whether it is a majority or in a minority? And also, when we are recommending certain say healthcare provider services, or some kind of a follow up, the connectivity, like people who want to have, suppose they are suffering for mental health problems, and they want to have a connected group. So are we able to link them to proper connected set of physicians, or their own community? So is there any bias involved in giving the recommendations? So how we can find that, and how we can, and why do we need that? First of all, because regulators have demanded that we should go with proof of privacy compliance. So all this, mainly for the healthcare sector, the data should be very much protected and confidential. And data protection officers and staffs have been responsible for have been playing a vital role in educating people that why privacy is needed. Individual consumers can come and ask, like, why should I give the data to your systems, and what all algorithms do you run, and how do you ensure that whether confidentiality of my diseases would be maintained? And also, to have the solution scalable, being scaled with different nodes, different distributed databases, Neo4j, and in a wider setup, that are be able to maintain both fairness and privacy if at a scale. And to show visual compliance, that I was talking about, the lineage, how the data or the nodes have changed over a period of time as the patient's diagnosis have progressed, or their diseases have been going at a better state. So we need to have a different, if you're thinking of from a business perspective, we need to have different marketing, CRM, customer surveys, online store, and at the end of it, at the base of the system, if we are trying to link the systems, where the data comes from, whatever processing we do on the data, and the data goes to the next step, we preserve the integrity of the data, we preserve the lineage and the privacy of the data. We need to look for reduced time of deployment and quick response to compliance, that we are complying to all the standards. Now let us touch base on privacy, look at the different aspects of privacy in graph algorithms before we go for a fairness and the demonstration. So as we all know that there have been so many cyber attacks, and attackers are always looking to intercept our models, be it any model, not only graph models. So in the graph models, what they would try to intercept and try to get information, it's about the nodes, as well as it's about the edges. They would try to get about which patient the data is, where does the patient, what is the age of the patient, or what is the salary of the patient. If all this information are getting stored in the nodes, so we need to be very careful how do we anonymize the data. And if you try to look at from the attacker's perspective, what are the different types of attacks? It could be active attacks, and or it could be passive attacks. Same like the person who knows, the attacker knows the information, that how the model has been trained, or has some idea, like the white box and for the black box, where the no information is known, and that attacker will continuously try to send some data, get some results, and try to do reverse engineering and try to map back that this data are actually present in the model or not. And the goal is, of course, it may be a twofold goal. For that active attacker, maybe non-id entity disclosure. For the passive attacker, maybe link identification. And these may vary from whether they want to either decipher the vulnerable links or the nodes. And what privacy operations, it can be any kind of anonymization. We will see some of the anonymization techniques, and as also differential privacy plays a vital role in anonymizing graph data. So, to start with, where Neo4j has helped us, so all these records where we are storing individual private information of the people, we have role-based access control, which gives a flexibility for the healthcare providers or doctors to have access to information what is relevant to for them. We did not have to uh, like de-anonymize or keep the raw data accessible to everybody. It will be based on roles, who needs what amount of information. And of course, the zero trust, if you know about the cloud zero trust principle, we should follow that, and that would enable us to give access on a stepwise manner, and based on the roles that each of the individuals in the 360 healthcare system plays. Fine-grained access, security of nodes, properties, and relationships, and multiple users to have different views, create different views of the same database. That's provided by Neo4j. And Neo4j, on top of that, when you diagnose a disease, a patient calls the call center. We need not disclose all the patient interactions or all the patient step-by-step diagnosis results to everybody. We can on top build on access controls using Kerberos and LDAP. And what is most important in today's industry is how do we scale, how do we do it at a minimal cost, and what is our efficient ways of scaling. So we can build several scalable schemas that can be enabled to build on premise graph databases or across, which can be also scaled across enormous shards that are spread across clouds and clusters spread across different geographical regions. And that is comes that Neo4j governance and data security for that comes embedded with Neo4j. Now, let us go to the concepts of we have talked about that we need to anonymize the data. So, how we can do the masking? So, here if you see that the original graphs has all the raw information. Now, going to the next step is we would mask a certain field, maybe like the name or the age. We need not Alice can be there will be several Alice present in this in a same hospital. But how do we anonymize the age? We can put some boundaries like A anonymity, T diversity, and all this anonymization features we can build in where we don't disclose the actual age or the actual disease of the patient. And that will help us in creating a perturbed version of the original graph. L diversity, K anonymity, and T closeness. So you can embed all those while creating the nodes of the graphs. Now, we can also build histograms and incorporate differential privacy. So this is called node privacy. So what it helps us to do, so we can remove a node, because the concept of differential privacy is like even if we remove a single node or a link age from a graph, the graph which you have used for your training the algorithm, like the graph neural networks, should not give any output that the attacker may be able to differentiate between the original graph and the ones which you have perturbed information. Means you have added a node, removed a node, or you have added an age, or you have removed an age from a graph, and that's the perturbed version of the graph. But whenever that graph is also trained using the all the different nodes and ages in the when the attacker attacks the graph, he or she won't be able to get any clue that this is the original graph and this is the perturbed graph. That's the role of differential privacy. And what we do, we have removed one node here, you see, and once the his degree histogram is nothing but the number of incoming ages that are coming to the node. So you see the first one, the first histogram shows that there are only one node which has six connections, but when I remove that, the number six is goes to zero. There's no goes to two. So there's the change in the degree of the graph in degree, what we call the in degree of the graph happens. So 06001 minus this is just nothing but addition of the in degrees of the graph, and what's the change is no 13, and then we compute the degree histogram under node privacy. What it aims is to prevent attacker from determining an individual, what are the secret records of the individual. Of course, this comes at a cost of accuracy, because this everything has a trade-off. Even if we want to target having responsible AI, it does not mean that we will build responsible AI and have an highly accurate system. But based on the business and based on conversations with the doctors and the diagnosis, we need to achieve at a respectable trade-off that we can offer when we build in differential privacy into the graph algorithms. And the what happens is it has to be robust. We also have robust metrics to test that how much robust is the graph. Same happens with the age. You removed an age AB, and then the in degree of the graphs has changed. The different nodes you see on the nodes histogram has changed. Previously, A has nodes. The degree of is 6, right? The 6 in degree with the node A has being all connected edges. Now you remove one edge AB, and if you see there is it's the degree is 5. So how many nodes have in degree 0, 1, 2, 3? You plot it, and then you try to decipher what is the degree histogram under age privacy. But there is a catch in it. So removing an age it changes the degrees by 2 in 2 nodes, effective 4 counts. So what we term this as a sensitivity is 4K, and under the K it's age privacy. But this is very not that much robust measure. It can be negligible for a large graph. That's why we go to another step up and we try to bring in noise calibration to global sensitivity, which is nothing but you add a node, you have seen that we have removed ages and we have built in differential privacy. Now we are trying to add one age which was not even present. So bringing in a neighbor node and giving some attributes based on the node's characteristics, and you recalculate all the age histogram value, right? And then you try to measure the what is the maximum change of query results when modifying one tuple. You have changed one tuple. What is the maximum change in query results? So this helps us, and you could create a nodes as simple like match one person, create and add that node with this properties. Noise, this is kind of a noise injection to achieve different differential privacy, and that can be calibrated according to the global sensitivity of the query. So how much noise you want to add to give the model a perturbation that will enable you to add it, and it will be measured by the maximum change in query results, right? Now we have talked, just going through quickly through the summary what we have talked about: the node age differential privacy, removing an age here, then node differential privacy, removing a node here, then age differential privacy, removing an age. Then we have outlink differential privacy, so remove a node which is faced outer to the graph rather than all the nodes which are into the graph. And also partition differential privacy, so neighboring graphs you can partition with a one disjoint subgraph, so you can remove the disjoint subgraph. And you whatever we do, we have to scale it. Well, how we can do that? So you have the original data, you have the bottom data, and that we call local differential privacy, because locally for each of the graphs you are adding noise, and which must be like differentially private, extending differential. So it's not only you can see the view of your graph, but you can see an extended view of the nearby nodes. That's called an extended local view. Yeah, and then you can compute the noise, assimilate the subgraphs also. If you have this local view of the graph and then an extended viewers of the neighboring graph structure, and that helps us to go and compute overall differential privacy for the graph which you are proposing. And are you able to scale it? Most important. And why we have looked for recommending privacy in graph networks. At the end of the day, our goal is to have recommendations built with graph algorithms for healthcare industry. So this does not change, the output doesn't change significantly. We are able to perturb the information, and we avoid the risk of data leakage that can come from GNN based personalization algorithms. Because at the end of the day, when we have these graphs fed into the GNN based personalization systems as the graph neural networks, right, we are at the risk of exposing the confidential information of the users. So you see, you have now, you are just removing, we are having those k anonymity, l diversity, t closure, you can incorporate that, and then you part of that information, you don't need the names of the person. Even you can go on one degree higher and not disclose sinus, but put it in a very generic medical information name. That won't be able to disclose that this person suffers from sinus. And this is an extended view that how your graph algorithms can be beneficial when you incorporate privacy in graph data before you go for one level high, that is, you insource all the data from different patient records, and then you build a larger extended federated graph GNN based personalized algorithms that is enabled to provide personalization or recommendation to different sorts of users. So there you may be needing various kinds of synthetic data, and you may, instead of just transferring the graph machine learning model parameters, you transfer the embedded vectors, right? And that can improve your efficiency and accuracy. So coming about graph machine learning model parameters, when you transfer that, there is another thing that you can even train these models locally. And while training, we will see that some of the filters we can apply, and to enable that this is also private, and the private models goes, and this at a larger scale, when you build a machine learning GNN based personalization, that is also a private algorithm. Of course, our goal is to build a robust and algorithm. Similarly, in healthcare, with graph neural networks and graph recommendations, what we can do, we can we have seen that, but we can also break it down to local subgraph. And local subgraph, and you incorporate privacy aggregate at a simple like a federated model. And on the other side, you can also give a feedback kind of a thing. You aggregate information from your neighboring subgraphs, and that also you encrypt the user embedding. You have the embeddings, we'll see about the embeddings, and encrypt the user id, right? And then we'll touch bit on privacy and see an example. So the main problem with graph data is this is non-identically distributed. Each node represents an individual. If you see that color of the nodes represent an individual, you can have represent different types of other minority groups through this different colors. So if you see, this is a typical problem, non-ID representation that you will see in a graph algorithm. They are not identically distributed, the graph database. And to handle that, your data will be it will be on two sides of your upper straight line, rather than it will be a mixed and a identically equally distributed. And to handle that, what we can do, there are different taxonomies, that kinds of fairness algorithms that you can incorporate, and you can build in non-id fair graph data. So you can go through this, and outside the scope that we explain everything. So what is our end goal? What are the principles that we should follow? So we should see the similarly situated nodes, or similar behavior of the individuals in terms of diseases should be treated similarly. Then we measure how this it's similar or non-similar in terms of different metrics, like Jaccard metrics, cosine similarity. Then we can have that to add another ranking, so that we can request similar rankings in inputs and output space, how this is different. Then cluster-based different individual fairness graph algorithms we can incorporate, where a representation graph where two nodes are interconnected are share same type of behavior, and the clusters are, we should be fair in terms of the types of node behaviors and the edges that are present. So similar type of nodes and similar type of edges should be clustered under one category corresponding to the other one, similar as clustering, but we do graph clustering, that is helps us to build in fairness. So of course that will help us to tackle all those fairness parameters, if you're aware of, on the statistical parity or equalized odds and disparate impact, and which will help us to tackle this problem not only at an individual level, where you can measure the individual fairness in compared to the group where the individual belongs, as well as a network level, where you can see that bias, you have to measure the bias of the variance recommendations that you're giving for a group of, say, people who are suffering for sinus. You're giving some recommendations, or doctors are following a category of treatment. So how do you do that? So this group fairness algorithms will help us to do. And we have talked about embeddings, if you remember. And there, when we have the embeddings, our goal is to filter the sensitive informations like gender, occupation, age, so that the output does not get biased with this kind of an information. So learn graph embeddings that is fair with respect to a combination of sensitive attributes. That's kinds of how we can do that. We can see the mutual information loss between sensitive attributes and embedding as zero, or we can incorporate some kinds of adversarial training filters for each of the sensitive attributes. And in Neo4j, what we can look for is debiasing. We will see one example, debiasing graphs. So whether you can debias based on your graph when you are pre-processing, add some kind of anonymization during the optimization technique, like page rank, some of the clustering algorithms we have talked about. You can also put up some of the features, and then measure your ROC, AUC scores, if one score. And post mining, like post processing, you can add different sorts, different types of processing techniques to debias your output, and then you measure the bias at the output. And why do we need fair graph recommender? It's because, see, offer unbiased recommendations. If there's a link, so interlink and intralink. Like as a healthcare provider, if we are giving users different sorts of information, independence of race, gender, and ethnic biases. So David should be freely able to contact to Sophia as well as the Adam. There should not be any bias that link when we predict the graph links, right? We are disproportionately predicting or connecting the members of overlapped representation overrepresented group. So we have majority information. Of course, we are also being looking and scrutinizing the data, that we are not over predicting or over linking the link prediction for the overrepresented groups. And when we see in terms of right graph convolution neural network, right, we have to see like how do we overall graph, how do we pass the neighboring messages to the GCN, the graph neural networks of the graph convolution network. So number of odd unordered nodes, sharing an edge with different number of nodes, nodes aggregation algorithms. So these are the some of the extra things that we need to be careful, so that the neural network is unbiased and we are able to identify same diseases and treatment patterns, lower the time of cost and drug development, as well as formed informed prescriptions when dealing with new diseases. Yeah, and this is one example. If you see the code, you have to write a GCN layer, and that's the place as engineers we are free to tube the graph and add as many of hidden layers or the features that we want to percolate to the end of the graph, or build the full neural network. And then how this graphs from neighbors we get the collected information. Yeah, so we have seen this is mainly the same thing, just to iterate the fact that same diseases, node classification and link prediction. So bias removal will in graph fairness training will help us to have fair treatment and node classification, fair node classification and link prediction. So this is an example with demonstration with Neo4j. Need to install the following libraries, connect the graph, create the Neo4j connection, and there is in an entity, if you have an entity database where you have the different partners who are collaborating, either healthcare provider, the user diseases, how the disease gets changed. This is a typical example. Like a certain medical treatment has occurred, a treatment has improved a medical condition, and then you are capturing all this information because it's improved or it has deteriorated, what medication has been prescribed to the individual, and then what problems did it offer at different states. The graph helps to, the Neo4j example helps to see at different states, capture the lineage and come up with the corresponding algorithm. And the Neo4j's primary role lies in creating responsible recommendations, that you run the contextual information and evaluate the connected data at different points. What information could be biased, could be overrepresented, could be you need to anonymize it, and then apply the machine learning models from patient going to hospital, treatment start, cause and effect of medication, that are, and determine the probability that a patient is likely to be cured, and store these relationships and the outcomes to predict new situations, tracking for validating decision and reject counterintuitive recommendations. Sometimes we make false predictions. And at the end of the day, it's being responsible based not only fairness and privacy, but also to be flexible, accurate and responsible, and to create sustainable solutions, that we are having the proper lineage of the recommendations. So this is another example where you can create the, you have the training data. So what you will do, you will give the model name, and this example shows how you can create the embeddings for the diseases, drugs, patients, and all the patients. Three embeddings goes together, and you take the data from different ontologies, drug bank, the patient medication history, and you train that. And the embeddings helps you to jointly heterogeneous graph, and the jointly trained embeddings helps you to scale and provide better recommendation from a document classification. And this is another example that you have can see that you have got the data from medical entity prediction model and UMLS knowledge base, and you have predicted heat burn, chest pain. You can perturb the nodes. You don't need male, female, and to perturb the ages to give a final recommendation. Yeah. So there are some of the references, and I would like to show you uh, another screen where if you feel free to contact me. The Yeah, there's a collab notebook. Just feel free to ask questions if you have any. So what you need to do, you need to install all the relevant libraries. I will quickly walk through the notebook and take the NLP data where you have different sorts of graph histories or graph lineages stores. You need Neo4j, of course, and then what you do is you have the different sentences in the entity recognitions algorithms run, and you ultimately develop a entity, right? The sequence of events that is happening. Connect with Neo4j's graph database, and have the checks that whether it is properly installed or not, and then you try to contact and get the actual batch, like how you would want to develop the algorithm. So this is the password. This is all for Neo4j connection, and then you do a visualization. How does your graph look like? What are the diseases? Who are the individuals? What are the different sorts of treatments you are following? And then you can see how all the admission has happened, that what is overlapping with what events, what are the medications that has been applied, it's just insulin or a pancreatic disorder, and then when he's been admitted, when the patient has been discharged, which date has been, all these events you have done, and then you have come up with a entity based model, and then you go for the it's to go for the, you want to add some constraints, you want to add some pre-processing for the fairness part of it, do that, and then at the end of the day you will get an algorithm, and you can do the offer the recommendations. So more post-processing, fairness, and privacy you want to incorporate, feel free to do that. So it's not possible to walk me through the entire notebook, but feel free to reach out if there is any question you want to have, and then you can just have this algorithm feed in, and then on that build of the algorithm, predict new outcomes that you would like to know that is not possible. Feel free to do that. Yeah, questions?